Thank you, and a very good morning, or a very good afternoon, or a very good evening in whichever time zone you are at the moment. I would like to begin by expressing my gratitude to the organizers of the International Conference on Advances in Construction Materials and Structures, ICCMS 2021, especially to Dr. Blesson Thomas for inviting me to become a keynote speaker for this event. What I'll be discussing today is actually on elastomeric polymers for protective application of concrete structures subjected to impulsive loadings. Okay, the impulsive type of loadings that we are going to talk about is in the range of blast and impact loading. My name is Sudharshan Raman, and I'm actually an associate professor in the civil engineering discipline at Monash University, Malaysia, and my email is actually shown. So before I actually commence my keynote lecture, I would like to thank my collaborators. A lot of this work has been undertaken jointly with them, especially Dr. Chandima Somaratna, who was my former PhD student. Currently, he's actually attached to the University of Jaffna, Sri Lanka. I would also like to take this opportunity to express my gratitude to Dr. Damit Mohoti at UNSW Canberra, my PhD supervisors, Professor Priyan Mendis and Professor Tuan Ngo at the University of Melbourne in Australia, as well as to my collaborators at UKM for many years, Professor Khairia Badri and Dr. Azrul Mutali. What I'll be presenting to you today on this topic is actually a culmination of more than 10 years of work, where we actually looked in detail and comprehensively regarding the application of two types of polymers, which I will be discussing today. So there are three main aspects which have been highlighted in this title that I'll be stressing on throughout this presentation. One is on elastomeric polymers, and then the use of the elastomeric polymers for protective application, and the type of loading that they will be subjected to are impulsive loading, which are blast and impact type. So this is actually the outline of my presentation. I will introduce the topic, talk about impulsive loading, which are blast and impact, mainly blast and impact nature. Introduce the polymer coating technique. Okay, introduce the polymer coating technique. I'll be discussing mainly on two types of polymers, which is polyurea and polyurethane. Okay, and then I'll be presenting the findings. I'll discuss on the work which has been undertaken with polyurea as well as with polyurethane, and then discuss the findings separately. And finally, I will actually summarize the work. Okay, structures across the globe nowadays, they face different type of hazards. Okay, technical hazard. It can be natural hazard, it can be man-made hazard, as well as accidental hazard. What we will be discussing today will focus on blast type of loading and impact type of loading. But before that, I will also be talking about the synthesis. In some parts of my lecture, I will also be talking about the synthesis of the material. Okay, type of accidental blast loads are caused by gas explosions, chemical explosions, as well as terrorist attack from car bombs or truck bombs. Okay, impact, it can be accidental, light aircraft fragments, or even vehicular impact, or due to man-made events such as terrorist activities related to missile and aircraft. Okay, there are also some explosion associated due to fire. Okay, but we will not be touching on that in this lecture. So before we go on to look at the behavior of different type of materials, so let us talk about time dependency and loading rate. Okay, as you know, when you are talking about blast and impact loading, they are actually different from quasi-static loading, where the loading rate is actually much higher than what you can actually observe during the quasi-static loading. Okay, but the factor or the parameter which is actually influencing the behavior of the material is actually the strain rate. Okay, the strain rate, and this subsequently will also influence the response of the structure when they are subjected to such type of dynamic loadings. Okay, so to introduce or to show the importance of retrofitting or strengthening works, I will actually bring you to one event which happened in 1995, on 19th April 1995 at the Oklahoma City in the US, regarding this event of Alfred Murrah building bombing. Okay, in this event, there were two sections of the structure. One section was totally collapsed. The other section was actually it did not collapse, or it was able to stand without collapsing even after it blast. So what one of the major findings from the investigation was that in that collapsed section, okay, out of the 175 occupants, 153 were casualties. A lot of the casualties were actually in the collapse section, or 87% of the occupants in the collapse section were actually casualties, whereas in the uncollapsed section, only 5% of the occupants were casualties. What does this imply? Had the structure resisted the blast load, the casualties could have been a lot fewer. That means if the structure had resisted the load, and even if the structure was damaged, but if it did not collapse, the casualties could have been a lot lower. So this actually provides highlights the importance of retrofitting or strengthening works for structures which can be subjected to impulsive loadings. Okay, let us look at the definition of blast load. Okay, Mace and Hayden, they have actually defined blast load as a process of very fast chemical reaction producing transient air pressure waves called blast waves. Another definition of a blast load, which was actually provided by Remenikoff and Caroline. This is a definition or description that I usually use in my presentation, is large-scale stored energy, which is released rapidly, parts as thermal radiation, as well as in shock waves in the form of blast wave and ground shocks. So there are three components here: thermal radiation, blast wave, and ground shocks. Okay. And in a blast load, there are two main parameters which define the severity of an explosion. The first one is actually the charge weight, and then the standoff distance. The charge weight is actually measured as an equivalent weight of TNT. Standoff distance actually refers to the distance from the target or the explosive to the structure. Okay. And the peak pressure from an explosion is a function of the standoff distance of the target, okay, R, divided by the cube root of the charge weight, W, which is actually measured in the equivalent mass of TNT. Okay, and it's actually called the factor of scale distance. The scale distance actually defines the severity of a blast load. Okay. When you talk about impact loading, it is actually influenced by various factors such as the force, velocity, as well as the time dependency or the strain rate of the strain rate which is induced during the event of impact. Okay, different type of impacts induces different type of impact load. For example, what is shown in the graph on the right is due to an aircraft, different types of aircraft that you can see. Okay, but we may think that, okay, these are not very commonly happening in our daily life. In reality, they can actually happen quite commonly, especially when you are considering vehicular impact, as shown in the next slide. It can be induced by some of the structures which can be subjected to such damage include the bridge piers of overhead passes, which are prone to vehicular impact. Okay, this can happen anywhere. Okay, it can happen in any parts of the world. These are accidental impact loading. Okay, or bridge girders and beams of overhead transportation structures against impact from a vehicle. You may have watched it in some videos where if a vehicle passes, a slightly taller vehicle passes, and it cannot doesn't have the if the bridge girders does not have the sufficient clearance, there will be impact from the vehicle onto the structure. These are also commonly observed or they can occur in a normal situation as well as critical infrastructures, critical water infrastructures, which can be exposed to impulsive loading for accidental blast or impact effects. And these can actually cause significant damage, not only to the structure, but also to the economy of that area. Okay. So as we have highlighted, these are some of the common occurrence, and from the Alfred Murrah case that I've discussed earlier, I've actually highlighted why protection of structures is actually important against such accidental or man-made impulsive events. Okay, so when we talk about protective technologies of these structures, the current practice at this stage are mainly focused on the use of fiber reinforced polymers. Okay, fiber reinforced polymers, for example, are like carbon FRP, glass FRP, aramid FRP, as well as some hybrid FRP applications. Okay, but these composite laminates, they do come with their own sets of limitations, especially when they are subjected to blast event or impulsive loadings. Some of their limitations are actually shown here, listed here. They have low failure strengths. Okay, and when you want a structure to be strengthened against blast and impact loading, you would expect it to be to have high failure strain rates. Okay, practical installation challenges to existing structures, and they can also sometimes fail in premature condition, premature brittle failure due to debonding or concrete cover delamination, FRP and concrete cover delamination. And sometimes they come in, usually these FRP composite, they come in FRP wraps, they come in excessively thin layers. So you need impractical number of layers or wraps when you want to strengthen a structure effectively against such impulsive loadings. So this is where a group of researchers in different parts of the world started looking at alternative materials to FRP to strengthen structures or to retrofit structures when they are subjected to impulsive loading. And it was hypothesized that materials with high failure strain values may perform better in retrofitting these structures. This is how these two materials came into play, polyurea and polyurethane, where we started looking at it some time back. Okay, and they have elongation capacity of more than 100%. And some of the advantages are the elastomeric. They have high strain capacity. In our case, we notice in quasi-static condition, the strain can actually go up to 300%. They are highly ductile. They have the ability to shield and contain concrete debris and fragment during the blast event. Okay, they act as a membrane to protect the debris and fragment from propelling. We have the ability to tailor their properties at ease, and they can also be applied easily onto the structure by using spray-on or brush-on technique. So these materials, polyurea and polyurethane, has been used in the construction industry for different applications, mainly for waterproofing applications in the past. Okay, so this is actually an alternative to the use where we start looking at it from a protective application type of use. So initial work on this was undertaken on lightweight steel structures as well as unreinforced masonry structures by Knox, Davidson, and his group in the US as well as Baylor. Okay, this was in the early 2004-2005, and then subsequently there was a group in Australia as well as in the US. They started looking at this material for steel structures and plate. Okay, and they were also investigated for composite system by different researchers, including one of my collaborators, Dr. Mohoti, where he started looking at composite aluminum plates. Okay, we started looking at this application for concrete structures sometime at the end of 2007-2008. We started off with polyurea. Okay, one of the important aspects that has to be investigated in detail due to the use of these polymers is the behavior at high strain rate. And this has been investigated by various researchers over the last 15 years. We should say 15 years. And some studies are actually published very recently. And what it has been found in most of this publication or most of this work is that some common properties of this material, they are highly nonlinear and rate sensitive. They exhibit significant hysteresis behavior during loading and unloading cycle. Okay. At the same time, it was also observed that they transition from a rubbery-like behavior at low and intermediate strain rate to leathery-like behavior at higher strain rates, which means that their E value or Young's modulus becomes higher when they are subjected to a higher strain rate. The material actually stiffens at higher strain rates. Okay, this is one of the major observations of this material when they are subjected to high strain rate loading. Okay, our work in this area was initially by using polyurea, and their high strain rate behavior, high strain rate properties was published in the journal Materials and Design in 2013. This is the first part that I will be discussing today in this presentation. Okay, so in this study, what we have used is actually an Instron VHS 8800 high strain rate testing system. And the setup is actually as shown in these diagrams. where the lower grip is actually the moving grip. Okay, it's in motion, whereas the upper grip is actually a fixed grip. Okay, and then based on the testing, we tested it at quasi-static condition as well as various strain rates. This is the quasi-static properties, the engineering stress strain curve of the polymer, where it has a strain, it can go up to strain of close to 300%, which is the highest strain was recorded was actually 2.98. And then when we tested it at different higher strain rates, this is the true stress strain curve of the same material in the quasi-static condition. And then these are the quasi-static properties that were recorded during the experiment. The density was about 950 kilogram per meter cube. The elastic modulus was close to 50, 49.5. And then the strain at fracture was actually 2.98. And as you can see, the material actually exhibited strain hardening behavior after the yielding point. And then when we tested it under different strain rates at increasing strain rate up to close to 400, we noticed that the E value, okay, the initial elastic properties of the material actually stiffens when the strain rate is actually increased. Okay, when the strain rate is increased, the material actually stiffens, and this is the true stress strain curve of the material polyurea that we tested. Okay, and this is actually available in this publication in Materials and Design from the year 2013. So what we did subsequently was to model the dynamic increase factor of the on different parameters. In this case, for the DIF of modulus of elasticity, we have used the Cowper-Simons correlation, and then we have actually developed a material card to be used in Elastina for the numerical work. What we have used here is actually material plasticity polymer, or MET89. So to summarize the major findings from this work, the stress strain range that we have actually tested in this case, we looked at from 0.006, which represents the quasi-static condition, up to about 388. The polyurea is actually highly ductile, where its elongation capacity is actually more than 100%. The stress strain behavior is considerably non-linear, and it exhibited significant rate dependency, and we have classified this material behavior as rate dependent, linear elastic piecewise, linear strain hardening material. Okay, and one of the major observations here, we found that the modulus of elasticity is actually enhanced with the amplification of strain rate, or the material actually stiffens when the strain rate are actually increased. And then the same material we actually applied, we tested it as a coating for reinforced concrete panel under blast loads, and these tests were actually conducted in the Mai Dak province in Hanoi, Vietnam, where we actually tested about 4 panels. The first panel had a slightly different dimension, and then UR2, unreinforced 2, it was a bare panel without any coating. PUB4, PUB10, and PUTB4. This represents different coating thickness and coating location. PUB4 is polyurea is actually applied on the bottom surface by 4 millimeters. PUB10 on the top surface, bottom surface at 10 millimeters. PUTB4 is a top and bottom surface, 4 millimeters on each face. Okay. So these were the panels which were actually prepared for the blast trials in Vietnam. And this is the top surface. Only PUTB4 was coated on the top surface, as you can see here. And then this is the bottom surface. Okay. And then this shows the fixing assemblies of the panels. They were actually connected by using bolts and cleat, by using some angle cleats and all those things. And then the bunker was actually designed with 100 MPa concrete, high strength concrete. And masonry brick walls were actually built around it, and our measurement devices were actually placed within this cavity inside of the test bunker. Okay, so these are some of the instrumentation that was used during the testing. And then this is the test setup, okay, and we used a special type of explosive, which is known as ammonite. Okay, this is the panel which is being tested, and then during the blast event. Okay, and subsequently we model the findings from, we model the same panels by using numerically model both the panels by using Elastomeric. And then the first stage, what we did was to determine the TNT equivalency factor for the ammonite blast. We have actually used two different softwares to actually characterize that, and which is Air3D as well as Convert. And then I will show an example of specimen PUTB4, which is actually found the top layer of polyurea. In this case, PUTB4 was different from the other panels, where in the top layer there were on the blast facing face there was no polyurea in the other panels, whereas PUTB4 had a polyurea layer of 4 millimeters. This is the result. This is the result for the specimen PUTB4. What we have actually obtained numerically, we have actually modeled the polyurea by using 6 different types of material models: material type 3, material type 7, material type 18, material type 19, 24, as well as 89. We found that material type 89 was the most. It gave the closest representation to the readings that we have actually observed during the experimental stage. And we also measured from the numerical model, we also measured the strain rate that were recorded in the polyurea on the blast facing face. This was the only panel which had polyurea on the blast facing face. So the strain rate that was recorded in this layer was actually 43, whereas in the concrete was about 10. Okay. And this was the bare panel. We have actually increased the load, so that the bare panels actually increase the load in the numerical model, so that the bare panel actually fails by direct shear. Okay, this is the bottom face of the panel, and in a polyurea coated panel by 4 millimeters, what we initially observed was that the polyurea layer was actually still intact. Even in the test, we did not notice any tearing of the polyurea, and we did not notice any debris and fragment being propelled. Okay, and then when we remove the layer, we can actually see that, of course, the damage mechanism has been changed, but the debris and fragment actually, there was no debris and fragment which was actually produced, mainly because the polyurea layer was still intact. And then we also tried to model the reduction of thickness in the polyurea coating. These were actually almost similar to what we actually observed during the experimental stage. So the major findings that we have actually got here is that from this blast trial is that the retrofitted panels recorded much reduced displacement as well as reduced crack widths compared to the bare panel. And the polyurea coating contributed positively in enhancing the blast resistance of the panels. Okay, flexural crack formation, and there was no indication of shear crack formation. Of course, we tried to model direct shear failure in the numerical analysis. The polyurea bonded well with concrete, but we did not test the bonding characteristics in this stage of experiment. And the application of coating on the blast facing face was more beneficial compared to only coating it on the non-blast facing face. Subsequently, in the next stage, we started looking at using polyurethane. So through my experience of using polyurea, there are some aspects that I thought that, okay, this has to be paid attention to when we started working on polyurethane. Here, we actually, we wanted to develop or synthesize our own polymer. So there was an active researcher in my institution at the time, Professor Khairia Badri, who was actually working on synthesizing different types of polyurethane. So I started communicating with her, discussing with her on developing this type of polymer to be used for retrofitting application. So the base material for this polyurethane was actually from palm oil. Okay. So we actually synthesized our own polymers, polyurethane in the lab in the Faculty of Science and Technology of University Kebangsaan, Malaysia. So what we did here was we actually synthesized our own polyurethane by using palm oil as the base material. The plasticizer was actually varied from 0 to 15%, and this actually we developed or we synthesized 8 different types of polyurethane. The designation that we follow here, for example, PU0 represents 0% plasticizer, PU15 represents 15% plasticizer. Okay. And then once we have actually synthesized the polymer, we tested their properties under quasi-static condition. As I said, there were 8 types of polyurethane that were synthesized from PU0 to 4, 6 up to 15. We characterized its chemical properties and the mechanical properties as well as thermal properties. In the mechanical properties under quasi-static condition that were actually characterized were density, Shorty hardness, flexural properties, Izod impact value, as well as tensile direct, and we also performed direct tensile tests. And these were actually published in the year 2016 in the journal Polymers. Okay, the entire comprehensive results were actually presented in this study. What we have actually observed, maybe I will just refer to the tensile graph over here, the bottom middle one. So we can see that as the plasticizer content is increased, the elongation capacity, okay, of the material increase, but the E value actually reduces. Okay, but at the same time, the material initially was indicating strain softening properties. Later on, they started showing strain hardening properties. Okay, so we wanted something in the middle. Okay, we wanted something which has got high elongation capacity, at the same time slightly higher E value. So we shortlisted 4 different polyurethanes, which is PU2, PU4, PU6, and PU8, to undergo further testing under high strain rates. Okay, under the second stage of testing, we selected the 4 types of polyurethane. We subjected it to direct tensile tests at 6 different strain rates, from low strain rates to intermediate strain rates. And we actually evaluated the tensile mechanical properties such as Young's modulus, yield stress, strain at yield point, tangent modulus, ultimate stress, failure strain, resilience modulus, and toughness modulus. And then we also looked at their loading and unloading behavior. Okay, so this is actually for PU2. As you can see, when the strain rate was actually increased, the elongation capacity actually reduces, whereas the graph on the right actually shows the loading and unloading behavior. Okay, this is for PU2, PU4, PU6, and then lastly PU8. Okay, we actually tested, as I mentioned, these 4 different polyurethane, and we shortlisted 1 to undergo further testing, which is PU6 with 6% plasticizer, to undergo further testing under dynamic condition, which is we tested the cyclic softening behavior at different strain rates at 0.001, 0.01, and 0.1. Okay, to look at the cyclic softening behavior of the material. So in the next stage, subsequently, we only use PU6 in all our experimental work. Okay. And then we also studied we also tried to characterize or develop, model the constitutive behavior of the material. What we did was we chose existing hyperelastic models, which are strain rate independent, Mooney-Rivlin as well as the Ogden model. And then we incorporated strain rate effects by using viscoelastic models of Cowper-Simons, Johnson-Cook, as well as our own proposed viscoelastic model to account for the varying strain rate. And then we developed a hyper-viscoelastic constitutive model for these polymers. You can actually find this in one of our publications, which has been published very recently in the year 2020. The second paper, which is actually shown here, hyper-viscoelastic constitutive model for predicting the material behavior of polyurethane under varying strain rates and the under varying strain rates. Okay, the high strain rate test was also published last year in a different article. Okay, so you can, if you need more further details on these findings as well as the testing details that we have used, as I've explained earlier, you can actually go through these publications. And then in the next stage, what we did was lab scale experiments by using concrete specimens of 40 millimeter, 40 by 40 by 160, where we have actually developed these specimens by using aggregates of aggregates of 10 millimeters. Okay, fine aggregate as well as coarse aggregate of 10 millimeters, and then we coated the polyurea coating PU6, the formulation of PU6 with different coating variations as shown. We actually tested 15 different coating configurations as shown here. We varied the coating location, coating thickness, as well as which surface they are actually coated. Okay, and we also we tested them under two strain rate conditions at 0.000033 as well as 0.067, just to look at the variation of strain rates. How does it influence the behavior of the coating as well as the bond characteristic between the coatings. The bond in this study, what we did was we studied the bond behavior between polyurethane and concrete under varying slipping rates or varying strain rates, but I would not be presenting those results here. This is one of the work which will be published in the near future. Okay. So in the scale concrete specimen experiments, what we have actually evaluated was coating thicknesses, coating position, as well as coating location. That means whether you're coating 100% the entire surface of the bottom layer, or only 75%, or only the central 25%. Okay. Okay, the combination of these three, there were about 50, as I mentioned, there were 15 configurations that we have tested under the laboratory condition, and the parameters that we have actually tested here are the maximum flexural stress, failure strain, strain energy density, as well as the nature of the cracks. Okay, and then we also modeled the findings by using, these were some of the findings that were observed. We also modeled them by using numerical models of Elastomeric. Okay, and in the last stage of this work, what we did was we took an existing experimental work, which is reported by Tanapundra Wikit et al. By using their work was actually focused on FRP strengthening of concrete panels, which were subjected to blast, and the panels were actually 75 millimeters thick. Okay, this was a work which was performed in Thailand with the University of Melbourne, and it was published in the year 2010. So what we have done is we have actually taken the data from these experiments and then the bare concrete data. So this is the model development, the blast wave parameters, blast wave propagation. This diagram actually shows the blast wave propagation and how we actually developed the finite element models. And then we undertook parametric studies in this study by varying the coating thickness. Okay, what we did was we modeled the bare panel and then we applied the coating. What we varied in this study was the coating thickness, coating position, mass concentration of coating on particular position, and influence of blast scale distance. And then we compared the findings of reduction in displacement, support rotation, as well as displacement reduction to the total depth. Okay. So, I will present part of the data here. Okay, this is actually the mid-span displacement of mid-span displacement time history of the finite element models of a controlled reinforced concrete panel with the displacement recorded during the blast trials. What is shown here is that when you see the full curve until the end, this is the experimental finding by Tanapundra Wikit et al. And what we model is actually shown in this dotted line at the top. And they were matching quite closely to the experimental data. So we took this model that we have developed, and then we started applying the different variations of coatings. Okay. For example, okay, what we have done is we have actually applied the coating on the impact face, on the rear face, as well as both faces by using different coating thicknesses. Okay, the uncoated here refers to the control specimen, and there was no, it was just a bare panel. 1.875 we constitute to 2.5% coating on the impact face, up to 15 millimeters, which is 20% of the panel thickness. Okay, so we can see here that when the coating is actually applied on a single surface, coating on the rear surface was actually more beneficial for the coating on the rear surface, was actually more beneficial for the panel. Okay. The next stage, we actually looked at the coating thickness in terms of reduction of displacement, support rotation, as well as displacement reduction to the total depth of the panel. And we found that when you're actually coating it on the rear surface by using this type of polyurethane, is actually more beneficial to the panel. Okay. Lastly, we looked at the coating position, and even for different thicknesses, we found that coating on the rear surface was actually more beneficial. So what we can see here is that this is actually looking at the mass concentration. Okay, this exhibits that the support rotation is actually significantly lower when you coat it on the rear surface for the same mass concentration. Reduction of displacement is higher when they are coated on the rear surface, as well as when you compare the displacement reduction due to the total panel depth. Okay, so in all cases, we can see that the when you're actually coating on the rear face, it shows a more beneficial effect. Okay, what we have actually modeled here is actually we have used matte monofibrillin rubber, and then we have incorporated the high strain rate properties of the polyurethane that we have found from our experiment. So what we found here was that matte 27 or matte monofibrillin rubber provided reliable computational similarity to simulate the dynamic behavior of the polyurethane. The findings compared reasonably well with the findings of Kanapurravi et al. But when we look at the coating location, they influence the level of protection offered significantly, and from this finding, we can conclude that applying the coating on the rear surface with respect to the loading was more effective than coating on the impact face. But the benefits of coating on both the impact face as well as the back face or the rear face is actually demonstrated in this chart, that when you coat it on the front face, it actually provides enhancement to the capacity against compressive and shear failure, and it reduces the compressive crack propagation. Whereas when you coat it on the back surface, it enhances the tensile and shear failure, reduces tensile crack propagation, displacement, and also reduces displacement and deformation. And one of the major effects which is actually observed here is that it reduces the fragmentation or debris propagation, especially when they're subjected to blast and impact loading. So if you require more details on some of the work that we have actually undertaken, these are some of the recommended readings that I would recommend to you. Besides the publication that I've actually highlighted throughout my presentation, this is one of the review papers that we have actually published in 2018, which looks at the use of polyurethane for structural and infrastructural engineering applications. Okay. As well as this publication, which was published in 2015, which looks at the application of elastomeric polymers for blast and ballistic retrofitting of structures. Okay, this is another publication that I would recommend you to look at. Before I end my session here, I would like to acknowledge again my collaborators. The funding for this work was actually provided through a Ministry of Higher Education Malaysia funding, through an ERGS grant, which was awarded in 2013. I would like to acknowledge the Ministry of Higher Education Malaysia for providing this funding to undertake this work. I would like to acknowledge Dr. Chandima Somaratna from University of Jaffna, Sri Lanka. Bulk of this work on polyurethane was actually undertaken during his PhD. Dr. Damit Mohoti, who has been my long-term collaborator in this research. Professor Priyan Mendes, Professor Tuan Ngo from the University of Melbourne, Dr. Tung Pham from University of Civil Engineering in Vietnam, who actually supported me during the experimental trials for blasts by using the polyurea coatings, as well as my research team at UKM, Professor Khairiyah Badri, Dr. Azrul Muttalib, as well as Professor Norazman Muhammad Noor. I would also like to record my acknowledgement to Monash University, Malaysia, my current employers, who have actually supported my participation in this conference. With that, I end my presentation, and I thank you very much.